Yeah, okay. It is time to continue the first session of our workshop, and our next speaker is here, and the floor is yours.
Thanks, Elena, for the introduction. I'm very happy to give a talk here. Today, I would like to talk some recent results on graphs with a high degree of symmetry. In this talk, I will mainly say something about four kinds of symmetry of graphs: homogeneity, homogeneity, and factorizations of graphs with of some homogeneous graphs, and quasi semi-regular symmetric graphs. Now let's look at the definitions. Let GAM be a simple graph with vertex set V and edge set E. A symmetry, sometimes called automorphism of a graph GAM, is a permutation pair on its vertex set V, such that UV is an edge of GAM if and only if U to pay, V to pay is an edge of GAM. All automorphism of a GAM form a permutation group on the vertex set called the automorphism group of a GAM, denoted by AutoGAM. Usually we use the automorphism group to describe the symmetry of a graph. Roughly speaking, the more symmetry a graph has, the larger its automorphism group will be, and vice versa. We are mainly interested in the problem about the classifications of families of graphs with a high degree of symmetry. In each case, we may impose a symmetric condition P, and then we may attempt to describe all graphs with given this given property. For example, vertex transitive is a kind of a symmetry. A graph GAM is said to be vertex transitive if for any two vertices U, V of a GAM, there exists automorphism R of GAM such that alpha sends U to V. Actually, this is a bit weak symmetric condition. There are many examples. In particular, we can give a large class of vertex transitive graphs by the Cayley graph. Cayley graph is divided in this way. Given a finite group G and an inverse closed subset S of G, which does not contain the identity of G, the Cayley graph, Cayley GS, is a graph with vertex set just this group G, and every element in the group G is adjacent to SG. Here, the little s belongs to the capital S. And it's not difficult to prove that every Cayley graph of a group is vertex transitive. So we have a large class of vertex transitive graphs. And actually, some well-known graphs are Cayley graphs. For example, the circle of length n is a Cayley graph. For example, it's a Cayley graph of the circular group Zn with respect to this set. And also the dimensional half cube Qn is a Cayley graph. It can be read as a Cayley graph of the elementary abelian 2 group of order 2n with standard basis of this group. And also the complete graph Kn is a Cayley graph. And the complete bipartite graph Knn is also a Cayley graph. And actually we have many other examples. Also, there are some vertex 20 graphs which are not Cayley graphs. For example, the Peking graph is a vertex 20 but not a Cayley graph. Except the Peking graph, we still have a lot of such a lot of other vertex 20 graphs which are not Cayley graph. There are far too many vertex 20 graphs for us to stand a chance to achieving a classification. So we may need some more stronger symmetric condition to vertex 20 graphs. Now let's look at the homogeneous graphs. A graph is called homogeneous if any isomorphism between any two isomorphic induced subgraphs extends to automorphism of the whole graph. This is maybe the strongest symmetric condition. You can see two isomorphic induced subgraphs extends to automorphism of the whole graph. Here are two examples. Pattern. This graph you can easily prove is homogeneous, and also every complete graph is also homogeneous. Actually, homogeneous graphs are very restricted. There are some other examples. For example, the line graph of K33, the line graph of the complete bipartite graph K33. Siha obtained the classification of a finite homogeneous graph. The result is a finite graph is homogeneous if and only if it is isomorphic to one of the following graphs. The first graphs are finitely many disjoint copies of the complete graph or its complement. Except to these infinite families, there are also two sporadic ones graphs. One is pattern, the other is just this the line graph of K33. So you can see the examples for homogeneous graphs are rare. The next symmetric condition is so-called set homogeneous. A graph gamma is called set homogeneous if any two isomorphic induced subgraphs are equivalent on the autogamma. Here, by equivalent we mean for any two isomorphic induced subgraphs, there exists at least one automorphism of a gamma that sends one graph to the other subgraph. By the definition, we can say every homogeneous graph is a set homogeneous. But for the finite graph, the converse is also true. Actually, Gardner proved the following result. In this, Gardner gave a classification of finite set homogeneous graphs, and also all of these graphs are just the homogeneous graphs. You can see finitely many disjoint copies of a complete graph KR or its complement, and the pentagon and the line graph of a K33. So even we the homogeneous to set homogeneous, but the examples are also there. Next, we have another symmetry called the connected homogeneous. A graph is called connected homogeneous if any isomorphism between any two isomorphic connected induced subgraphs extends to an automorphism of the whole graph. In this case, we just require any isomorphism between any two isomorphic connected induced subgraphs extends to automorphism of the whole graph. So by definition, we can see homogeneous must imply connected homogeneous, but the converse is not true. For example, this graph, the cycle of length 6, this graph is connected homogeneous, but it's not homogeneous. Because you can see, for example, this vertex and this vertex induced disconnected graph to K1. Also, this U and W also induced disconnected graph K21, but there exists no automorphism of the cycle of less that can send UV to UW. So this graph is not homogeneous, but it is connected homogeneous. And similarly, we can prove the Peterson graph is connected homogeneous, but not homogeneous. Actually, Gardner obtained the classification of a finite connected homogeneous graphs, and all the connected homogeneous graphs are listed in this theorem. We have 6 class of graphs. Anyway, even for the connected homogeneous graphs, we can see. First, let's look at the S homogeneous or S set homogeneous. Let gamma be a graph. Let S be a positive integer. Let G be a subgroup of autogamma. Gamma is called GS homogeneous if every isomorphism between two isomorphic induced subgraphs on at most S vertices can be extended to an automorphism, say G of gamma, so that G belongs to the little g belongs to capital G. So we just require the subgraph has all the at most S. In this case, we call the graph is GS homogeneous. Okay. Similarly, the graph gamma is called GS set homogeneous if any two isomorphic induced subgraphs of a gamma of order at most S are equivalent on the G. Here we also require the induced short graph has order at most S. Here we give two new countable symmetry in graphs, and when S is 1, by definition you can see one homogeneous graphs and also one set homogeneous graphs are just vertex transit graphs. So in this case, there is no hope to obtain a classification. But when S is big, for example, if S is 5, then 5 homogeneous imply homogeneous. This means for S is 5, this symmetry is very strong symmetry. And for S is 4, we have this. The only finite 4 homogeneous but not 5 homogeneous graphs are the sloppy graph and its complement. So in this case, you can see every 4 homogeneous graphs, every 4 homogeneous graph is the sloppy graph or its complement all homogeneous. For 4 homogeneous, the graphs are also very restrictive. And when S is 3, Cameron and Maxson gave an explicit list of finite 3 homogeneous graphs. There are some infinite families in this case. And finally, for the 2 homogeneous, by definition, we can see a connected 2 homogeneous graph is either a complete multi-partite graph or an orbital graph of a primitive permutation group of a rank 3. So to give a classification of a 2 homogeneous graph, it suffices to give a classification of a primitive permutation group over rank 3. And actually, these groups can be classified by in several papers, maybe 130 pages, several papers. So in some sense, 2 homogeneous graphs are also known. This is some result about S homogeneous graphs. Now let's look at some result about S set homogeneous graphs. De Villers proved that finite 5 set homogeneous graphs are set homogeneous, and by Gardner's theorem, we know every set homogeneous graph is homogeneous. So this means every finite 5 set homogeneous graph is homogeneous. And in the same paper, Douglas also proved that the only finite 4 set homogeneous but not 5 set homogeneous graphs are just the sloppy graph and its complement. As we already know, these 2 graphs are also 4 homogeneous. So from here we know 5 set homogeneous imply homogeneous, and 4 set homogeneous imply 4 homogeneous. So how about 3 set homogeneous and 2 set homogeneous? Actually, for the 3 set homogeneous case, we have this result. Every 3 set homogeneous graph is 2 homogeneous. But is three-set homogeneous graph three homogeneous? Yes. Applying this theorem, we obtain the following result. A finite graph is a k-set homogeneous. Here k is a positive integer. If and only if it is k homogeneous. Yes. You can see when k is at least 4. Yes, from David's result we know this is true. So we just use this theorem and based some group theory, and we can for proof for k is 1, 2, 3, we can obtain this result. The main case is k is 2 or 3. This is some result about S-set homogeneous graph. Another kind of symmetry is the so-called S-connected homogeneous. Also let gamma be a graph and S a positive integer, G a subgroup of auto gamma. Then we said gamma is GSCH. By CH we means connected homogeneous. So GSCH means every isomorphism between any two isomorphic connected induced subgraphs on at most S vertices can be extended to an automorphism, say G of gamma, so that this little g belongs to capital G. This is a definition of a GSCH graph. By definition, you can see if S is 1, G1CH just a vertex graph. And if S is 2, graph is 2CH, if and only if it is 1 arc-transit. For these two cases, the graphs are too rich to give a classification. So the first interesting case is 3 connected. S is at least 3. And also we note that a graph of Gauss at least 4 is 3CH if and only if it is a 2 arc-transit. And for this case, 2 arc-transit graphs have been extensively studied in the literature. So we will mainly consider 3 CH graphs with Gauss 3. And here we mentioned a result of Gray, which gives a classification of infinite 3 CH graphs with more than 1 end. Now, for S is 5, we prove this result. Any locally finite connected, locally connected 5CH graph is homogeneous. Here, locally connected means for every vertex, its neighbor, the induced subgraph by the neighborhood of a vertex over every vertex U. The induced subgraph is connected. Then we mean the graph is locally connected. So if we require the graph is locally finite and connected and locally connected, then 5CH imply homogeneous. And also for S is 4 with the same requirement, 4CH graphs is a 4CH graph is either homogeneous or is isomorphic to one number following graph, the Slavic graph, the McLaughlin graph. We also in the same paper we also some results about locally disconnected 4CH graph, but still needs further research. For the this is some result for the 4CH graph. For the 3CH graph, we first prove that a connected graph gamma is a G3CH if and only if G is a vertex sensitive on gamma. And for a vertex U of a gamma, either the local action of a GU on gamma U, that is the subgroup, the permutation group induced by GU on gamma U. Gamma U is just the neighborhood of a U in gamma. This permutation group is two transitive, or this permutation group is of rank 3, and the growth of gamma is 3. So this means give a characterization of a G3 CH graph in terms of a local action. And with this theorem, we can further prove this the next result. Suppose that gamma is a connected G3CH graph, which is not complete multipartite. Let N be a normal subgroup of a G, which is intransitive on V gamma. Then either the quotient graph gamma N is just K2 by edge, and gamma is a G2 arc transitive. In this case, gamma has growth at least 4. And or the quotient graph of gamma by normal subgroup N is G, the quotient G over N 3 CH, and gamma is a normal cover of gamma N. So with this theorem, we can see the class of finite 3CH graphs of Gorges 3 is also closed under taking normal quotients. Mainly we consider here. Because we just see for this case, the graph is has growth at least 4. So for the Gorges 3 case, you can see the quotient graph is still 3CH, and the original graph gamma is normal cover of the quotient graph. So this class of graphs is closed under taking normal quotients. This makes us can consider the quasi-primitive 3CH graphs. A transitive permutation group G on a set omega is said to be quasi-primitive if every non-trivial normal subgroup of a G acts transitively on omega. And by on a Scott-Prager theorem, finite quasi-primitive groups are classified into 8 classes. Here will introduce 5 of these 8 classes. Actually, these 5 types will be important in study of G3CH graphs. That is HA, AS, SD, PA, and TW. Now let's look at definition for these 5 types of Cauchy primitive graphs. Sorry, there's 5 types of Cauchy primitive graphs. Now let G be a Cauchy primitive permutation group on a set omega with a unique minimal normal subgroup N over G. If N is an elementary abelian group and acts regularly on omega, then we say G is of type HA, holomorphic. In this case, G is also primitive on omega. The second case, if N is a non-abelian simple group, then we say that G is our type A is almost simple type. Below, we just let N be a direct product of some isomorphic non-abelian simple groups, say T to K, where K is at least 2, and the T is a non-abelian simple group. Here N, just remember, N is a unique minimal normal subgroup of G. If N is not regular on omega and has a regular normal subgroup, with point stabilizer isomorphic to T, just the full diagonal subgroup of N, then we say G is of type HD. And if any proper normal subgroup of N is not regular on omega, then we say that G is a type TA. If N acts regularly on omega, then we say G is of type TW. Now let's look at the theorem about Cauchy primitive 3-stage graphs of Gorges 3. Suppose that gamma is a G3CH graph, which is neither complete nor complete multipartite, and G is a Cauchy primitive on V. Then G is of a type HA, AS, ASD, PA, or TW, and examples exist for each of these types. Just mentioned a result by Shell on 2-arc transitive, Cauchy primitive 2-arc transitive. In the 2-arc transitive case, the G has type HA, AS, PA, or TW. But for the G3CH case, we have this type. But for this type, actually we only have 4 graphs. This is some result about 3 connected homogeneous graphs. Next, I will talk about some result about relative to homogeneous graphs. First is about factorization of some homogeneous graphs. It mainly consider a partition of the edge set of a graph with highly degree symmetry into some disjoint subsets, say E1, E2, Ek, and such that the subgraphs VE1, VE2, and VEK are pairwise isomorphic. For example, when K is 2, we just obtained the self-complementary graph. A graph gamma is said to be self-complementary if it is isomorphic to its complement, gamma C. Here is an example. 4-vertex graph, you can see, is a self-complementary graph. And also, you can check the 5-vertex cycle graph is also a self-complementary. The study of self-complementary graphs maybe goes back to 1960s. And up to now, various aspects of self-complementary graphs have been studied extensively by many authors. Much of the work has been focused on the conjunctions of a self-complementary graph with specific symmetry properties. For example, Peschert in 2001 obtained the classification of vertex and edge-centered self-complementary graphs. Actually, we only have 2 infinite families: Paley graph, or a graph with similar conjunction with Paley graph, or a graph of all the 23 square. Another factorization just about called almost self-complementary graph. Let gamma be a graph of an even order. Gamma C is just the complement of a gamma, and I is one factor of a gamma C. Let me say that the graph obtained from gamma C by removing the edges of I is almost complement of gamma, and denoted by this. The graph gamma is called almost self-complementary with respect to I if it is isomorphic to its almost complement. From the definition, you can see almost self-complement graph, complementary graph is just factorization of a complete multi-part graph with n parts of a size 2 in two isomorphic graphs. Here is an example. The cycle of length 6 is almost self-complementary graph. We give a classification of edge-sensitive almost self-complementary graphs. A connected graph gamma is edge-sensitive almost self-complementary if and only if one number following holds. First, gamma is just the cycle of length 6. Second, gamma is the cube. The third case is gamma is the lexicographic product of X with K2 C. Here, X is an arc-sensitive self-complementary graph. So X is known by Peschert theory. And the fourth graph is just the antipodal cover, antipodal 2 cover of the complete graph of Q plus 1. By definition of almost self-complementary graph, we know this is just this kind of graphs is just a factorization of a multi-part graph with S part of a size 2. And also in 2007, Judici Lee and Potoniki and Xiao posed the following problem: determine all arc-20 homogeneous factorizations of the complete multi-part autograph with S parts of size T. So this theorem gives a solution to this problem in case T is 2. Now let's look at another kind of symmetry. First, look at this graph. This is just the 4-dimensional folded cube. It's also the half of the graph of a 5-dimensional cube. This graph is a connected homogeneous. Its automorphism group is just the semi-direct product of Z24 by the symmetric group S5. And this graph is actually such a Cayley graph. It has such an automorphism alpha. You can see this. This automorphism has only one vector point, and has 3 cycles of length 5 in its cycle decompletion. Such kind of automorphism or such kind of permutation, we will call it Cauchy semi-regular permutation. Formally, we have the definition. A permutation group G on a set omega is said to be Cauchy semi-regular if G fixes a point, say alpha of omega, and is semi-regular on omega minus alpha. This is the definition of a Cauchy semi-regular permutation group. Then a non-identity permutation G on set omega is said to be Cauchy semi-regular if the subgroup generated by G is Cauchy semi-regular on omega. In some sense, Cauchy semi-regular permutation is a generalization of semi-regular permutations. In 2013, these 3 persons initiated the study of graphs with a Cauchy semi-regular automorphism group. They give some conjunction and characterization. And some years later, these 5 persons classified cubic symmetric graphs with a Cauchy semi-regular automorphism. It turns out such graphs are rare. Actually, there are only 3 such graphs: the complete graph K4, the Peking graph, and the Gorges graph. 3 small graphs. This is for the cubic case. And recently, Yin and Fang classified the tetravalent symmetric graphs that has a Cauchy semi-regular automorphism. It turns out every such a graph is a Cayley graph on a abelian group of order. This is for the tetravalent, and very recently we characterization of a pentavalent symmetric graph for the very semi-regular and very automorphism. We have such a result. Let G be a connected pentavalent symmetric graph with a Cauchy semi-regular automorphism, then the following statements hold. First, if gamma has a solvable arc-truncated group of automorphism, if and only if gamma is one of these three graphs. We don't give the detailed conjunction of these two graphs. This graph is just the four-dimensional folded cube. For this graph, has order 2 to 8. This graph has order 2 to 12. So if the automorphism group is solvable, then we only have three graphs. When gamma is T arc-truncated for a non-abelian simple group T, then we have gamma is either the complete graph K6, or gamma is one of these gamma. Here also omit the detailed construction for these graphs. We only have 7 graphs. But here you can see T is a non-abelian simple group. Actually, we can see we can further prove every such graph is a normal graph of one of these, and for this case, we can prove there are infinitely regular covers such that every cover graph has a semi-regular automorphism. So for the non-solvable, for the parallel symmetric graphs with a non-solvable automorphism group, there are infinitely many graphs which has a cosy semi-regular automorphism. And finally, would like to pose some problems for further research. The first problem is about finite locally disconnected four stage graphs. So give a characterization or classification of such kind of graphs. And secondly, I think it would be interesting to classify finite locally connected 3CH graphs. And another interesting problem, I think, is to classify finite primitive 3CH graphs. Especially classify, for example, primitive orphan 3-stage graphs. Actually, for the two arc-transitive case, Cell and even have obtained a classification of primitive orphan two arc-transitive graphs. That's I think that's all I want to talk. Thank you very much.
Okay, thank you very much for the interesting talk and for sharing known results with us and showing some open problems on this topic. Are there any questions? There is a question from Natalia Maslova. Natalia.
Elena and Jin-Xin, many thanks for your wonderful talk. And I have a question on the definition of SCH graph, you have defined SCH graph, GSCH graph, which
Yeah.
depends on the group G. And what is just SCH graph without group?
Thank you very much. A good question. For the SCH, I just mean G is orthogonal. G is equal to the automorphic group of GAM. In this case, we will omit G. Just say the graph is S connected homogeneous.
Many thanks.
Thank you.